Welcome to the channel. So in this video I'm going to show you the wildfire detection analysis and vegetation change mapping using VIIRS and Landsat 8 imagery in Google Earth Engine. So now let's get started. So let me explain about the wildfire detection analysis. So wildfire detection analysis refers to the process of identifying and monitoring the wildfire using remote sensing technologies and algorithms. The analysis can be done using satellite data such as from the MODIS, moderate resolution imaging, spectroradiometer, and VIIRS, visible infrared imaging radiometer suite, and Landsat images. These platform provides a crucial information about the fire location, spread, intensity, and behavior, allowing for an early detection and monitoring and assessment of the wildfire. So the data sources that is available for the wildfire detection analysis: first, the satellite sensor like MODIS, VIIRS, Landsat, the commonly used wildfire detection. These sensors captures the data in thermal, infrared, visible wavelengths, making them effective in detecting the fire hotspot, temperature anomaly, and smoke plumes. And thermal infrared. The thermal infrared bands are the key for detecting heat signatures from fire, as they identify the high temperature regions that corresponds to active flames. And optical sensors, they help visualize the burn scars, smokes, and vegetation affected by the fire. So the key indices that are used are the normalized burn ratio to assess the burn severity. NBR is calculated using a near infrared and shortwave infrared bands to differentiate between the healthy vegetation and burned area. And next is a fire radio. The fire radiative power measures the radiative energy emitted from the fire, providing an insight into the fire intensity. And next is the brightness temperature. The high temperature pixels and thermal bands signals a potential wildfire areas. So now let me get back to the Earth Engine. So to perform the wildfire detection analysis and vegetation change mapping using the following datasets, first we have to define a region of interest. So to define a region of interest, first we have to define a variable called coordinate wildfire. So I'm going to select this particular study area here. So now we're going to place a point data over the map here. For that I'm going to use this tool called add a marker. I'm going to place a marker here. So I'm going to place my marker here. So once I have placed my marker, so you can able to view this section here. We have created a variable called geometry, the point data, with the latitude and longitude of this particular study area. So once you did that, we're going to click this option here to show the generated codes. So I'm going to copy this latitude and longitude of the study area here. So once you copied this, I'm going to paste it here. So I'm going to paste it here. So paste your latitude and longitude here. And after that, to create a study area, we define this variable called wildfire point equals to geometry.points coordinate wildfire, referring to this particular variable containing latitude and longitude. So to create our region of interest, we are going to use this particular global administrative boundary. So for that, let me show you the datasets here. So this is a dataset, global administrative unit layer. So the dataset availability is from 2014, and the dataset provider is UN. And this is the following code to access this particular dataset. So it provides us the country's boundary layer with its administrative units layer that is available in this particular dataset. So to access that, so I have defined this variable called boundaries equals to feature collection, that is Earth Engine feature collection, and referring to that particular code here to access the data. So FAO and 2015 level 1. So we are using level 1 dataset here. And next we define this another variable. So from the point data we have mentioned with the latitude and longitude using the specific variable here. So we have placed it. So we're going to filter out only this particular portion of this that is California. So to filter only the California, we have used this particular dataset that is our administrative boundary layer. So now we define this variable called region equals to boundaries dot filter bound wildfire point. So the wildfire point, which refers to this particular point here, using this point we're going to filter only the California here. So for that we are using this wildfire point, so referring to this particular point data with containing latitude and longitude. So we are going to filter with the specific wildfire point. And next we're going to define dot map function. So next we define .map function feature. So in that we return our feature .simplify function. So the simplify function is specifically used here. Let me show you the layer section here. I'm gonna click this country's boundary layer. So you can able to visualize this is the global administrative boundary layer. So in that we're gonna specifically select this particular study area. So this particular study area, that is our California in United States of America. So to filter this particular study area, we had defined this point here. So now to increase the speed of processing, so we defined simplify and mentioned as a 10,000 in order to reduce the number of vertices in each of this boundary here, for example. So we have now selected this particular study area using this point data. So basically we have reduced the number of vertices in this study area polygon here. You can able to see that in order to increase the speed of processing in Google Earth Engine. So for that we are using this function called simplify 10,000. So we are reducing the number of vertices in this polygon, that is California state here. You can able to see here. So next we're gonna navigate to. So next we're gonna center our layer. So for that we define map.center object region referring to our California state here with the zoom level. And to add this layer we define map.add layer region with the default visualization parameter and output the layer as region of interest. So now you can able to visualize it here. So this is our country's boundary layer, the global country's boundary layer, and this is we have filtered using the point data, that is California state in United States of America. So next we're gonna load our VIIRS wildfire data into our Earth Engine. So for that we define this variable called VIIRS data equals to image collection NASA VIIRS 002 VNP09GA. This is the code which you can able to access as wildfire data. We're gonna load our VIIRS and wildfire dataset into Earth Engine. So for that we define variable called VIIRS data equals to image collection NASA VIIRS 002 VNP09GA. So in that we're gonna select these two bands I1 and I2, and let me show you the details about the specific dataset here. So this is our VIIRS surface reflectance daily of 500 meter and 1 kilometer. We have two different spatial resolution for this dataset. So we have 500 meter as well as we have 1 kilometer spatial resolution. So the dataset availability is from 2012 to 2024. And dataset provider is NASA. So you can access this particular dataset using the specific script here. And these are the following bands that is available in this dataset, starting from M1 to M11, which is of 1000 meter of resolution, showing different wavelengths here. And similarly we have this other set of bands, that is I1, I2 and I3, has a spatial resolution of around 500 meters. You can able to view this band here, and the wavelengths are given here. So let me explain about this particular dataset here. So the VIIRS surface reflectance daily 500 meter and 1 kilometer. So this dataset is a daily product derived from visible infrared imaging radiometer suite on board with the Xiaomi National Polar Orbiting Partnership satellite. It provides atmospherically corrected surface reflectance value for each pixel, which accounts for the effect of an atmospheric gas aerosol and Rayleigh scattering, making it more accurate for analyzing surface properties such as vegetation, soil and water. So the key characteristics are the resolution. The dataset provides two spatial resolution at 500 meters and 1 kilometer, making it suitable for an application that requires a moderate spatial detail. Next is the temporal coverage. This dataset covers a daily surface reflectance data, ensuring a continuous and frequent record of the surface condition, which is crucial for monitoring rapid environmental changes. And bands. The surface reflectance product includes multiple spectral bands that covers a different part of the electromagnetic spectrum, such as the visible, near infrared and shortwave infrared, providing a wide range of data for analyzing the various surface properties. So now let me get back to the Earth Engine. So from the dataset here, let me show you this. So the VIIRS wildfire data, in that we're going to select this two bands, that is I1 and I2. So the I1 and I2 has a spatial resolution of here, that is 500 meters. Compared to the other bands, it has a good spatial resolution, so it is around 500 meters. So we're gonna select I1 and I2, and we're gonna filter with the specific timeline. So this is the timeline where the wildfire has taken place in the California state. So it's 2017 October 8, 2017 October 10. So to visualize the details of this particular dataset, we have defined print VIIRS data. So let us visualize the dataset in the console section here. So in the console section, you can able to view this particular image collection, NASA. So I'm going to click this. So here we can able to see that it is a features list. We have 2 images for this specific study area. So let me show you that. So this particular image is taken on this date 2017 October 8. You can able to see that. And similarly, this particular image is taken on 2017 October 9. And we have 2 different images here for the specific study area. So you can also see the bands here, I1 and I2. Let me minimize it. So let me get back to with this area. So we're going to add this layer into Earth Engine. So for that we define map.add layer VIIRS data dot 2 bands function. So we're going to stack our layer because we have 2 satellite images that is available for this specific timeline. So to stack this image, we are using this particular function dot 2 bands, and dot clip, so referring to our region of interest, that is the study area, dot clip region, and with the default visualization parameter, and output the layer as VIIRS wildfire. So now let us visualize this particular layer here. Let me navigate to the layer section here. I'm gonna click this layer called VIIRS wildfire. So it's gonna load our this fire data into our Earth Engine. So you can able to visualize this particular layer here. Let me zoom out and let it load it. So the image is getting loaded here. That is our fire data, wildfire data. So now we're going to navigate to the layer section, and I'm going to click this option called this particular option here, and you can able to see here. So we have 2 images. So one image referring to our I1 band, and the second image referring to I2 band for the 2 different dates here, date October 8 and October 9. So I have set as an October. So from here you can able to visualize we have 3 different bands here. So RGB, red, green and blue region. So in that I'm gonna select this particular timeline, that is the I2 band 2017 October 8, and in that next I'm gonna select 2017 10 October 8 I1, and similarly I'm gonna select 2017 10 October 8 I2. So we have created a multi-band composite layer using the stack function. So let me adjust the contrast here. We're going to adjust stretch the contrast to around 90%, and so once you did that, so we're going to click apply here. So we're going to visualize the image here. So we have created a false color composite using the multiple bands here. So for example, we have selected this this particular band, that is I2, and I'm going to select this particular band I1, and similarly I'm going to select this band I1 here again, and we're going to stretch to contrast to stretch 98%, and we're going to click apply it, and let us visualize the result, another false color composite image. So now here in this false color composite, basically we have selected a date on 2017 October 8 here. So we can't able to find any fire areas here. You can't able to find any fire areas. So we're gonna shift to the next date here. So we're gonna select 2017 10 October 9 here. I'm gonna select this time here, and for the blue, for the green and blue region, I'm gonna select this particular band 2017 10 9 and I1, and similarly I'm gonna select the blue region. I'm gonna select this particular 2017 October 9, and I'm gonna apply the stretch type to around 98%, and I'm gonna click apply here. Gonna click apply. So now in this image, you can able to see previous image in October 8, that is in October 8, there was a vegetation was around here in this area, and now this particular region you can able to see the difference here. Let me zoom in. So now here you can able to visualize this particular area, the smokes that is you can able to see here in these areas. And similarly, you can also visualize the smoke also in these areas too. So now you can clearly able to see the burning areas. It is clear, you can able to see. So this smoke area which indicates the regions are under fire, which is clearly indicated in this data set here on October 9. And also you can able to see the smoking also released into the atmosphere. So it is directed towards in this direction here. You can able to see towards the north west direction. You can able to see the smoke. Let me show you the band composite again here on October this particular here. This is October 9. I'm gonna select on October 8 now. I'm gonna select October 8 and this one and October 8, and we're gonna stretch to 98% and we're gonna apply it. So we're going to visualize this image now, that is October 8. So this October 8 has doesn't have any burned areas or smokes or detected in these areas. It is completely void of any burned areas. But in October 9, let me click this and we're going to select October 9, and I'm going to stretch to a 98% and I'm going to apply it. And now you're going to visualize the burned area on October 9. So you can able to clearly visualize the detail here which is indicated. So these are the smoke areas, and you can also see here, and you can able to see it is completely affected by this particular area is completely affected by this wildfire here. You can able to see. So using this particular dataset, you can able to easily identify the wildfire locations. For example, this particular study area, the wildfire area has been highlighted, that is indicated in this part of this area, and also in this part of the areas where it is affected by the wildfire. So now we're going to select this particular study area. So we're going to navigate to this option called draw a rectangle, and I'm going to draw a rectangle over the study area and covering this section here, and I'm going to exceed this. I'm going to click and I'm going to drag it here, and I'm going to drag up here. And once you've created your study area, so you can also edit this particular one here. I'm going to drag this, I'm going to reduce this area, and I'm going to make it this area. Make sure I'm going to cover this part of this areas. So once you created your study area using this particular option, that is draw a rectangle. So now you have this latitude and longitudes are generated here. So in this section here, I'm going to click this. So you can able to visualize this latitude and longitude. So now I'm going to copy this latitude and longitude of the study area, and I'm going to paste it here. So now let me copy the latitude and longitude. I'm going to click this option. So we're going to copy this section here, and I'm going to copy this latitude and longitude, and now we're going to paste it here. And let me align this. So for the further analysis, we have selected only this portion of this area here. So we have managed to create a study area, and we have pasted our latitude and longitude in this area. So to define a coordinate for an area to analyze the vegetation and vegetation changes, we define this variable called coordinate area equals to, and we specify the latitude and longitude. So now to create a polygon, we define a variable called vegetation area equals to geometry.polygon quad area, referring to this particular variable containing latitude and longitude of this particular study area. So now to add this layer into Earth Engine, we define map.add layer, vegetation area, and default visualization parameter, and output the layer as study area. And to center this particular layer, we define map.center object vegetation area. So now we're going to run this code. We're going to click run here. So let me turn this off. So next we're going to focus on our new study region, so this particular area here. So this particular study area was under the wildfire situation here. You can able to see from this image here. We have shown in I have shown you earlier the smoke areas which reflects this particular study area is under wildfire. So next we're going to use our Landsat 8 image. We're going to compare the wildfire situation before the fire event. So the fire event which has taken place in this particular study area, California state, was around in October 9, 2017. So we're going to compare the previous year in 2016 and 2018, the before and after wildfire. So for that we're going to load our Landsat 8 image into Earth Engine. So and we're going to check how the vegetation has changed before and after this wildfire. So to do that, we have to load our Landsat 8 data into our Earth Engine. So for that I have defined this variable called Landsat before equals to image collection Landsat LC08 CO T1L2, and in that we're going to select this particular so let me show you the Landsat data here. So this is our Landsat 8 level 2 collection 2. So dataset availability is from 2013 to 2024, and the dataset provider is USGS, and this is the code to access this particular dataset. So these are the following bands that is available in this dataset in Landsat 8 image. So the resolution of this particular dataset is 30-meter resolution. You can able to see from here, and we have to apply some scaling factor, so and also the offset factor. So we have to apply scaling in and offset factor to our Landsat 8 image, and each of this band can be accessed by mentioning this particular band name, that is surface reflectance B1 and SRB2, SRB3. So you can access this particular set of bands using this set of names here. So let me get back to Earth Engine, and now here we have defined dot select SR dash dot star here. So this means that this is a regular expression that matches any sequence of character that followed that prefix SR dash in regular expression. For example, dot here represents matches any single character, and the star here which represents a 0 or more occurrence of the preceding characters. So in this case the SR dash dot star matches any band that start with SR and it's followed by any other characters. So basically we are referring to this particular sets of bands here. We are referring all these bands, this thing here. So for that we have mentioned as SR dash star dot star. So to access those band we have defined like this. So reason we have mentioned the details here, and to next we're gonna filter with specific timeline. So to view the before and after fire events, that is before and after the wildfire. So to do that we defined this particular timeline. So dot filter date 2016 January 1 to 2017 December 31st. So the wildfire has started in October 9 of 2017. So in order to view the previous, that is before and after effects, so we have defined 2016 January 1, 2017 December 31st. And next we're going to filter with a specific month here. So for example with the calendar range. So to do that we define dot filter Earth Engine dot filter dot calendar range. So we are specifying the day and the month, and we are represented it as a month here. So it means it is a day and this is the month, October 8. And next we're gonna filter with a specific study area. So this is the first study area here. So we're gonna filter with that study area. So for that we define dot filter bound vegetation area. And to add this layer into Earth Engine we define map dot add layer Landsat before dot median function, and we defined dot median function dot clip vegetation area. So vegetation area represents our study area. So this is our study area. So why we are using a median function instead of mean function? So let me explain about it. So why is a median function is better than mean? So the median is less affected by extreme values. It represents the middle value of the sorted data. So it remains stable even if few values are unusually high or low. And in case of mean, so in the case of mean is highly sensitive to outliers, and single extreme value can significantly change the mean, leading to a skewed or misleading representation of dataset. So for example, if you're analyzing the brightness of pixel in satellite imagery, there are some very bright pixels. Example, due to the noise or the cloud, the median will give a more accurate central tendency because it ignores the influence of those extreme values, while the mean might be pulled towards the brighter values or the extreme values. So let me get back to Earth Engine. So to add this layer, we define map.addLayer Landsat before dot median function dot clip for represents our study area. This is our study area. And to create a visualization parameter for our study area, we set the minimum and maximum value for the study area. So the minimum and maximum value here represents the brightness and the contrast of this image. So you can adjust your minimum and maximum value according to your choice. So I have made up a most suitable brightness and contrast of this image, that is for Landsat 8. So this is the range for it. So I mentioned it, and the bands we're gonna use are the SR-B5 and SR-B4 and SR-B3, and we're gonna output the layer as before fire RGB, that is in so let me show you the bands we are using here. So the band 5, which is our near infrared, and the band 4 that represents the red band, and band 3 is the green. So let me get back to Earth Engine. And now similarly to we're gonna load the Landsat data after the fire. So we're gonna filter with a specific timeline from 2018 to 2019. So for that, we define this variable called Landsat after equals to dot image collection Landsat LC CO T1 and L2. So similarly, we dot select SR dash dot star, and we're gonna filter with a specific timeline from 2018 January 1 to 2019 December 31st. And next we're gonna filter with a specific calendar range. So for that, we defined dot filter Earth Engine dot filter dot calendar range. We're gonna specify the day and the month. So we are specifying the day here. So we are specifying the day here, that is 8th, that is day, and the month, that is 8th October, and we are representing it as a month. And based on that, we are filter with the filter bound, that is based on the study area to filter. So we define dot filter bound vegetation area, which represents our study area, this new study area. And to add this layer, we define add after fire image to map in Earth Engine. We define map.addLayer Landsat after dot median function dot clip vegetation area, and we have set a minimum and maximum value, that is brightness and the contrast level of this image. And the following bands have been selected, that is SR-B5, SR-B4 and SR-B3 in near infrared. And this is B4 and B3, or the B4 it is red and B3 is green band and Landsat 8 image. And output the layer as after fire RGB. So now let us visualize this result here. I'm gonna navigate, click the run option here, and I'm gonna navigate to this option here. Let me turn this on before fire. So now we can able to visualize the image. So now we can clearly able to visualize the image here. This is before fire wildfire image of Landsat 8. I'm gonna turn this off, this layer, so we can able to visualize it more clearly. And this is our it's loading. So this is the Landsat 8 image before the wildfire. And let me turn on the after the wildfire. I'm gonna turn this on after fire. So you can able to see there is a significant change in the color contrast here. Let me turn this off, and you can able to see. So you can able to see this is the before fire, and this is after fire. So after fire, you can able to see this part of the areas has the vegetation has been significantly reduced in this part of this area, which is highlighted in this color here. Let me show it once more time. Gonna turn this off, and you can able to see that. So you can also compare this with fire data, that is the wildfire VIIRS dataset here. So I'm gonna turn off the before fire. So let me show you this after fire. This is before fire image, And I'm gonna turn on the after fire, and let us visualize this. This is the fire data of from this NASA fire data. I'm gonna turn this off, the Landsat. So this are the areas were affected by the fire, and this wild forest areas. You can see the smokes here, and after the fire event, you can see this data. So the fire has started from here and is spread it to almost to this entire areas, and also this area is also affected by it. So fire started here and it spread in this way and covering almost the entire stretch of this areas here. So clearly which highlighted these are the areas are affected by the wildfire. So we're gonna perform more further analysis. So next we're gonna calculate the NDVI before fire and after fire event. So we're gonna make sure that we're gonna see that NDVI before the wildfire and NDVI after the wildfire. So from the previous image of Landsat 8 image, you can able to see. Let me turn this off. So the red areas which indicates the vegetation cover, and the darker areas which indicates the burn areas. So we can able to compare before and after image here. So it is completely covered with vegetation. And after the wildfire, so these are the areas, darker areas represents the burn areas. So next we're gonna perform towards calculating the NDVI before and after the fire event. So next we have to perform our NDVI analysis, vegetation change mapping using NDVI indices. So before performing our NDVI indices, first we have to apply our scaling factor. So in our previous Landsat 8 image, we can able to see. So we have added our after fire image. So to view the details of those image, I have defined as print Landsat after dot first function. The first function here represents only to give the first image in that series. So let us view that in the console section here. So this is represented as after fire image. So this is the after fire image. I'm gonna click this arrow button here, and I click this property section, and here you can able to see the scaling factor to be applied before doing our NDVI analysis. So we're gonna navigate down here. So you can able to see there is a reflectance add band minus 0.2, and the reflectance multi-band represented as 0.000275. So you can able to see from this here we have this apply the scaling factor as well as the offset value here. So scaling factor is around 2.7.5 into 10 power minus 5, and this is the offset is minus 0.2. So we have to apply the scaling factor and offset value to our Landsat 8 image before performing the NDVI analysis. So for that we're gonna calculate the NDVI before the fire. So we're gonna apply first the scaling factor and the offset value. So we define this variable called NDVI before fire equals to Landsat before dot referring to this particular Landsat before image here. You can able to see the Landsat before image. So we are referring that variable, and dot map function img the image. So we have to now apply the scaling factors. First we have to apply this reflectance multi-band 5. So we have this scaling for reflectance multi-band has a scaling factor. All this band has a same scaling factor, so that is 0.000275. So we're gonna apply it. So to apply it, we define this variable called gain bands. Gain band 5 equals to earth engine. So to convert from a string to a number format, we are defined as earth engine dot number and image dot get. So to get represents get function we applied because we are referring to the metadata property of the Landsat 8 image. So we are referring to this particular property, meta property, that is reflectance multi-band and phi, or is all this value is similar. So we can refer this particular value. So for that we define image dot get reflectance multi-band phi. So it has a value of this particular 2.75 into 10 power minus 5 is this value. And next we have to apply the offset value to this image before performing the NDVI analysis. So for that we define variable offset band 4 equals to earth engine dot number, converting from string to number format. We are applying this function. So image dot get, so we are referring to the metadata property reflectance add band. So the reflectance add band has an offset of minus 0.2. So we are applying it. So image.get reflectance add band 3. And now to apply those, we define the variable. So to apply the scaling, the gain as well as the offset value, we defined a variable called scaled image equals to, referring to the image, we're going to multiply. So we define this variable called variable scaled image equals to, from the each of the input image we are multiplying the gain value, that is, so the reflectance multiband 5, so that is 2.75 into 10 power minus 5. We are multiplying with the gain value, and dot we are adding our offset value. So the offset value is around minus 2.0 to each of the image, and for that we define dot add offset band 4. So offset band 4 has a value of 0.2, and the reflectance multiband, that is the gain, has a value of around 2.75 into 10 power minus 5. Let me check that. So it has a scale factor of 2.75 into 10 power minus 5. So once you did that, we're gonna return the scaled image. So we're gonna return the scaled image dot, and we're applying the NDVI indices, normalized difference SR-B5 and SR-B4, and dot rename as a NDVI before. So let me explain about the NDVI. So NDVI represents the Normalized Difference Vegetation Index, is widely used to vegetation index for assessing and monitoring the plant health and the land cover and vegetation density. It is calculated using the red and near infrared bands of satellite imagery such as Landsat 8. So the formula, it is the NIR, that is near infrared minus red band, divided by the near infrared plus red band. So NIR represents near infrared and red represents the band 4 in Landsat 8 image. So the values here ranges from -1 to +1. So the value close to +1, that is 0.6 to 0.9, indicates a dense green vegetation. The value around 0 indicates a barren area such as rock or sand. The negative value indicates the water bodies or non-vegetated surfaces. So the high NDVI represents, that is from 0.6 to 0.9, represents healthy dense vegetation such as the forest, cropland or lush grassland. Or the moderate value here represents the from 0.2 to 0.5 indicates spare vegetation. Herbs or agricultural areas is in a less productive condition. So the low NDVI value from 0 to 0.2 may reflect the barren land, urban areas or land with a very minimal vegetation. So the negative NDVI lesser than 0 represents the water body or snow, as they observes the NIR and reflects the little or no red light. So let me get back to Earth Engine, and last we have applied as a dot median function. So let me explain why we are using median function again. So why the median function is better than mean? So the median is less affected by extreme values. So it represents the middle value of sorted data, and it remains stable even if few values are unusually high or low. So the mean is highly sensitive to the outliers, and a single extreme value can significantly change the mean, leading to a skewed or misleading representation of dataset. So if you are analyzing a brightness of a pixel in a satellite image, there are some very bright pixels. The median will give a more accurate central tendency because it ignores the influence of those extreme values, while the mean might be pulled towards those brighter values. So once we applied the NDVI before the fire, we have applied calculate the NDVI after fire event. So for that we define this particular variable called NDVI after fire equals to Landsat after, referring to the Landsat image of the after the fire event, and dot map function image, referring to each of the image, and we are applying the scaling factor. Variable gain band equals to EE, that is Earth Engine number, converting from string to number format, image.get. we are applying this gain band reflectance multiband value, that is 2.75 in 10 power minus 5, and the offset value we are applying here, that is Earth Engine number, image.get reflectance add value, that is minus 2.0. And to apply the scaling factor to each of the input image, we defined a variable scaled image equals to, this is the in each of the input image, img dot multiplying the gain band, that is 2.75 into 10 power minus 10, and offset value that is minus 2.0. We're gonna add that, and we're gonna return as a scaled image dot. We are applying the normalized difference for to calculate the NDVI after the fire event. So referring to SRB5 and SRB4, and we're gonna rename as NDVI after. So once you did that, we're gonna add this layer into Earth Engine. So for that, we defined here as a map.add layer NDVI before fire dot clip based on a study area. And so the vegetation here area represents our study area. So this is the study area that is affected by the wildfire. So we set a minimum to -1 and to a maximum of +1. So we have given the minimum and maximum value based on my NDVI values here. So the NDVI value typically varies from -1 to +1. So the value closer to plus indicates dense vegetation. The value 0 indicates the barren areas such as rock or sand. The negative values indicates the water bodies. So let me get back to Earth Engine. So we're given a minimum of -1 to maximum of +1. And the color palette starting from red, yellow and green area. So here the red will represents the water areas, and yellow will represents the barren or non-forest areas, and green will represents the forest areas. So similarly we define this output the layer as NDVI before fire, and similarly to add the after fire we define the similar function map.add layer NDVI after fire dot clip vegetation area minimum maximum value set -1 to +1. So the NDVI value ranges from -1 to +1, and the color palettes red, yellow and green. Red will represent water, yellow will represent all non-vegetative areas, and green will represent the vegetative area, and output the layer as NDVI after fire. So now let us run this code and let us visualize the result. So now here in the layer section we're gonna click the NDVI before fire. So you can able to see this, the NDVI before fire. I'm gonna turn off this after fire and before fire of Landsat 8 image. So I'm gonna turn down the NDVI before fire. So from the image you can clearly able to visualize the red areas represents the water areas, and the yellowish color which represents the non-vegetative area, and the green color which represents the vegetative area in the study area. And similarly you're going to turn on NDVI after fire. So you can able to see the difference here. This represents the water body, and there is a significant vegetation index, vegetative area has been reduced. So let me turn this and show you that. Now you can able to see that. So basically the fire event has started here, and it started to spread to almost the entire areas, and also towards in this part of this area you can able to see that, which is similar to that Landsat 8 image we had shown you earlier. So this is before fire, and this is it's loading. So this is after fire, and similarly this is NDVI before fire, and this is NDVI after fire. So now you can also change, you can also see the changes, NDVI changes in the histogram. So to do that we're going to define this particular print ui.chart.image.histogram NDVI before fire vegetation area represents our study area with a spatial resolution of 100. So basically we're going to compare the NDVI changes, NDVI before and after the fire. So first we have to visualize the histogram of NDVI before fire. So we define this print ui.chart histogram NDVI before fire represents our study area, the spatial resolution of 100, and dot set options we're gonna fix our. So we're gonna fix the title as the NDVI before 2016 to 2017, and the color of our NDVI have given this this set of color code will represent the blue color to our graph. So the represents the red color to our graph here. So this particular code will represent the red color to our graph, and H axis we define NDVI value, and the V axis we defined as a frequency, and the legend is none, and the bar group width of 95%. So basically reduce the bar width for the better visibility. And similarly we're gonna display the histogram NDVI after the fire. So for that we define print ui.chart.image.histogram we define NDVI after fire, referring to the variable NDVI after fire, and the study area, spatial resolution, and the set options titled NDVI after 2018-2019. And color, so this set of color will represent an orange color to it, to the graph, and h-axis NDVI value and v-axis is frequency, and similarly. So now let us visualize the result here. We are going to navigate to the console section here, and you can able to see the graph here. So now in the console section you can able to see the NDVI before fire and NDVI after fire. So this particular axis will represent the frequency, and this set of axis will represent the NDVI value. So we know that NDVI value with the positive value which indicates of vegetation area, and 0 value which indicates the bare earth or the rocky land, and the negative value which indicates the water areas. So you can able to see the values here, NDVI before fire, and you can able to see from this image here in the NDVI before, there's the value is comparatively is bit higher in before the wildfire. You can able to see from this image here, and in this case here in the NDVI after fire event, there is a considerable decrease in the NDVI value in this section, in these areas here. You can able to see that in this part of the areas where the frequency has been decreased significantly in this portion of this areas which is indicated here. So let us visualize it in more detail. So this is our NDVI before wildfire. So this is our NDVI value. So starting from 0 to positive, towards the positive, it indicates the vegetative areas. So this was the case in NDVI during before the wildfire. So this was the NDVI, and now similarly let us visualize the NDVI after the wildfire. I'm gonna click this option here, so you can able to see this difference here. So this is the NDVI before before the wildfire, and this is after the wildfire NDVI. You can able to observe in this portion of this NDVI value has been decreased considerably compared to this NDVI before wildfire. So you can able to compare the significant drop in the value in this portion of this areas here. Let me check in the after wildfire. You can see that value changes here. So in this portion of this area has NDVI has been dropped. This portion may indicates the wildfire affected areas where the NDVI has been dropped significantly compared to the before the wildfire. You can able to see the difference here. So now let me get back to our Earth engine here. So you can able to see the changes here. So there is a significant drop in the NDVI value in this portion of the section here. Compared to this area has a higher NDVI value, but the affected areas still have the NDVI value as lower compared to the wildfire before NDVI value before wildfire here. You can able to see the difference here. There is a decrease in the NDVI value in this section here, and also this portion. So next we're gonna calculate the NDVI change between the before fire and after fire event. So we're gonna subtract our NDVI before fire minus NDVI after fire to calculate the NDVI changes in that study region. So to do that, we're going to define this variable called NDVI change. So it is a simple technique just to detect the changes in NDVI value. We define that as NDVI before fire dot subtract, that is represents minus, that is NDVI before fire minus NDVI after fire to calculate the change in NDVI. So next, to add this layer, we defined map.add layer NDVI change dot clip vegetation area represents our study area, this part, this section, and we're giving a color palette. So the green which represents the no NDVI change areas, and the red which indicates the NDVI changed areas. So we're gonna output the layer as NDVI change. So now let us visualize this particular result. We're gonna navigate to the layer section here. I'm gonna right click this layer, and I'm gonna click this option called layer called NDVI change. So you can able to clearly visualize the result here. The green are the areas where there is no NDVI changes, and the red which indicates the NDVI changes. So NDVI changes has been clearly highlighted in red color. You can able to see from this image, and you can able to see the NDVI change here. But we have a little bit of problem in this NDVI change image. For example, I'm gonna turn this to a satellite mode here, or just me turn this off. So you can able to see there is a lake in this study area. So there is a lake port. So this is there is a lake here. So in the NDVI change is indicated as an affected area. So over the lake there might be a development of vegetation area, which has indicated in this NDVI image. So to mask out the water areas, next we're gonna, so you can able to see that this is the water area, that is a lake, and you can able to see here. So this portion is highlighted in the NDVI change. So now to mask the areas which are of water areas, so we're gonna perform some similar set of process here. So we're gonna apply the water mask to the NDVI change image. So basically we're gonna mask out this water areas in the NDVI image. So to do that, we're gonna define this particular variable called water mask equals to /image collection Google dynamic world cover. So basically this is a land use land cover data set here. Let me show you that. So you can able to see that this is a dynamic world v1. So this is the data we have access to mask out the water areas. So the dataset availability is from 2015 to 2024. So the dataset provider is World Resource Institute Google, and these are the different bands that is available in this dataset here. So you can able to see the bands here. We have water, trees, grass, flooded vegetation, crops, herbs, built, bare, and snow and ice, and we have a label. So we're gonna mask out the water areas. So we're gonna select this particular class called water. Let me get back to the Earth Engine here. So here you can able to, we have access the world dynamic, that is the land use data here, and in that we're gonna select label. So let me show you that. So you can able to see here. So this is a label class table. So you can able to see that. So this particular value, that is 0, which represents the water, and similarly the 1 represents the tree, and the 8 represents the snow and ice. So I'm gonna select this particular class here, that is water. So for that I'm gonna select dot select label referring to the dataset, and dot mode. So here we selected dot label dot mode function dot equal 0 dot not function. So I will explain this particular code in detail now here. Let me navigate to my board here. So I have defined as a variable water mask and /image collection referring to the dynamic world dataset here, and in that we have selected dot select label dot mode dot equal 0 dot not. So let me explain this particular dataset here. So the first set of code here referring to /image collection. So this loads the dynamic world dataset, which is a land cover dataset with 9 land cover classes at 10 meter resolution. This dataset is generated from Sentinel-2A Imagery and provides a near real-time land cover classification. So next we define dot select label. So the dynamic world dataset has a label band which contains a land cover classification as an integer. Each integer corresponds to specified land cover classes. So for example, we have shown it earlier that 0 represents water, and 1 represents tree, and the 2 represents grass, 3 crops, and 5 represents built up areas, and 6 represents the bare ground, snow and cloud. So we are applying this mode function. So applying the dot mode function, let me show you that. So we have applied dot mode, which represents the, so mode function takes the most frequent value, the most common land cover classes across all images in image collection. This is useful when dealing with multiple images over time and ensure that the most commonly occurring class at each pixel is selected, and thus filtering out the noise and transient land cover types. So after applying the mode, the result is a single image where each pixel represents the most frequent land cover class during the observation period, and followed by we have mentioned as dot equal 0. So you can able to see here I have mentioned as dot equal 0. So which indicates, so equal 0 checks where the land cover classes is equals to 0. So 0, which means the water. This creates a binary image. So the 1 represents water pixels, so the 0 represents non-water pixels. So we refers to equal water. which gives us represents the non-water pixels. And after applying this particular function, dot not function, so this not function inverts the binary image. After applying dot not function, the result will be true 1 for true, 1 for the non-water pixels, and false 0 for water pixels. So as a result, the non-water areas are masked as a true, and the water areas are masked as false. So this particular mask can be useful to exclude the water bodies from further analysis or focus on the non-water regions in the study area. So let me get back to Earth Engine. So once we have managed to mask out all the water areas, we have to add this layer. So for that we define map.addLayer, water mask dot clip vegetation area represents the study area, and color palettes we are referring to blue and red. So the blue indicates the water areas, and the red indicates the non-water areas. So output the layer as water mask false. So now let us visualize this layer water mask. So layer section, I'm going to turn this on, water mask. So now you can be able to clearly identify all the water bodies in the study area, which is indicated in blue color, and all non-water areas are indicated in red color. You can be able to see that. Let me turn this off. So all the water areas are clearly highlighted. You can be able to see here all the water areas are clearly highlighted in here in this image. And let us proceed towards our next. So next we're going to proceed towards the NDVI changes with the water mask. So basically we're going to mask out all the water areas in the NDVI image. So to do that, we define variable NDVI change masked equals to NDVI change dot update mask water mask. So the water mask refers to this particular layer. So it will mask out all the water areas now. So it's going to update our NDVI image and dot rename NDVI change masked. So it's going to mask out all the water areas in the NDVI image. So to add this layer, we define map.addLayer NDVI change masked dot clip vegetation area represent our study area, and the color palettes we given here blue, green, yellow and red here, NDVI change masked, and output the layer as NDVI change masked. And we're going to visualize this layer NDVI change masked, and I'm going to turn this layer on. So now you can clearly able to see that all the water areas been completely masked in this NDVI image here. You can able to see that. We're going to compare this with the NDVI change here, and let me turn this on. So this is the NDVI change without masking the water areas, and this is NDVI changes after masking the water areas. And after that we're going to proceed towards the exporting of a NDVI change image to a Google Drive. So now to export this NDVI changed image to a Google Drive, we defined export.image.drive image NDVI change masked clip representing our study area, description NDVI change masked, and the spatial resolution we are set to around 100, and the maximum pixel value, and the region represents our study area, which is represented as vegetation area, and the coordinate reference system. So we can navigate to the task section here, and to export this image we're going to click this option called run, and window pops up saying initiate image export. And to export this image, so this is a scale of 100, the reference coordinate reference system, and then the GeoTIFF file format. So you can just export this by clicking this option called run. I'm going to click cancel, and again I navigate to the console section here, and let me drag this down. And now we're going to display the histogram of the masked NDVI changes. So we defined the print UI chart.image histogram NDVI change masked vegetation area, and we are set to a resolution of around 1000. So in order to reduce the maximum pixel values, so it's going to take a longer time. So in order to do that, reduce that, we're going to mention as 1000 meter of resolution. And set options, we define NDVI change masked, and color, we define the set of color here. So it represents a green color to the graph here, and h-axis NDVI change value, and v-axis is the frequency. And let us visualize this particular graph here. I'm going to drag this in the console section, and you can able to see the NDVI change value here. So you can able to see from this graph here NDVI change masked. So here you can able to see the NDVI change value that is represented here, and this is the frequency. So after that, we're going to create a threshold mask for the area with the NDVI change greater than 1. So you can set a value of 0.1 as a main threshold to separate the burn area from the normal area. So we're going to separate the burn area from the normal area by creating a threshold of greater than 0.1. So to separate the burn areas from the normal areas, we define this variable NDVI threshold equals to NDVI change masked dot greater than 0.1. So we're gonna select all the areas, the burnt areas. So to do that, we define dot greater than 0.1. So now we define a variable called variable threshold mask equals to NDVI threshold, referring to this particular variable, and we're gonna update our threshold value to our image here. So to do that, NDVI threshold dot update mask NDVI threshold. So we're gonna update our values that is greater than 0.1. So it's going to display all the values that is greater than 0.1 to indicate the burnt areas. So now to add this layer, we define this map.add layer threshold mask.clip, referring to this this variable here, and .clip vegetation area representing our study area, and color palettes red. So red will highlight all the burnt areas in this study region, and output the layer as NDVI change greater than 0.1. So now let us visualize this result here. We're going to navigate to the layer section here and going to turn this on. So you can clearly view this image here. All the burnt areas are clearly highlighted in this image here. So you can able to see the burnt areas here. Let me navigate to this particular after fire event here. I'm going to turn this image on, and also I'm going to turn on this VIIRS wildfire. So let us visualize this first here. I'm going to turn this off. So you can able to see from this image here. So all the burnt areas are clearly highlighted in this layer here. NDVI change greater than 0.1. So you can able to see that. And let me turn this off. Gonna turn them on. You can able to visualize the burnt area in this study region. So this is our study region. And now in the next step, we're going to calculate the area of the burnt area in the study area. So the total amount of that is area were burnt during the forest fire. We can identify the total square kilometers. So to calculate the area of the burnt area in square kilometers, we define this variable called area in square kilometers threshold mask dot multiply image dot pixel area dot divide 1:10 power 6. So now we're going to explain this particular line of code in detail here for the understanding purposes. So here we define variable in square kilometers threshold mask dot multiply image dot pixel area function dot divide 1:10 power 6. So this is the binary the threshold mask is the binary mask created based on some threshold condition. Example, the pixel that meets a specific NDVI threshold. So in our case, we have defined threshold of 0.1. It is typically an image where 1 is true for 1 represents the pixel that meets the condition. Example, vegetation, water, or the other classification. So 0 represents a pixel, false, pixel that do not meets the condition. So it might be the non-vegetation or the non-water areas. And here image.pixel area. This function creates an image where each pixel contains its area in square meters. So in Earth Engine, each pixel have different size depending on the projection and the resolution of the image. Example, the Sentinel has a 10 meter and the Landsat has a 30 meter. So the image.pixel area function ensures that each pixel is assigned to its actual area. And divide 1:10 power 6. The pixel areas are originally in square kilometers, hence they are in 1 million square meters in square kilometers. Dividing the pixel area by 1 million and convert to a square kilometers. Basically, we are using this to convert the square meter to square kilometers. We are dividing by 1 million. And the threshold mask dot multiply. So the threshold mask is multiplied by a pixel area, that is square kilometers, and this multiplication is effectively retains the pixel value where the mask is 1 true and set the pixel area to 0 where the mask is 0. As a result, you can get an image where each pixel represents its area in square kilometers, but only for a pixel that meets the threshold condition. In our case is 0. Greater than 0.1. So output image. So the result is an image where each pixel value represents its area in square kilometers for region that meets the threshold condition, that is 0.1. We have defined value that is greater than 0.1. So let me get back to the Earth Engine here. So once it met the condition here, we're gonna further. So we are calculating the area of each pixel of this burned area. So that's why we mentioned the pixel area function, and to convert to square kilometers, we define dot divide 1:10⁶. And in the next step, so to calculate sum of all areas, we define the variable called total area equals to Earth Engine dot number. To convert from a string to a number, we define EE dot number, area in square kilometers, representing the specific variable here, dot reduce region. And to get a sum of all value, in the reducer section we define EE dot reducer dot sum to get the sum of all areas. And the geometry we represented as a vegetation area, this is the specific study area, and scale, that is we are set to a resolution of around 1000 meters, that is 1 kilometer. So you can also reduce the pixel to 500 or 100, but it will take a larger computation time. So in order to reduce that, I have increased the spatial resolution to 1000 meter. So for that I have mentioned as 1000 here. And last we define dot value function dot get 0, the first value here. So now to get the total area of NDVI change before and after the wildfire. So we do that, we define print area of significant NDVI change in square kilometers. So represents as total area here. So the output layer will be as total area. So we're gonna click this option called run here. So now we're gonna visualize the result here. So you can able to see in the console section the area of significant NDVI change in square kilometers. It is around 1760.62 square kilometers of area. So now we have managed to find out the total burned area in this particular study area, during the wildfire event in the California state. So the estimated areas to be found to be around 1760.62 square kilometers. So now let us take a look at the application of this particular study here. So these are the following applications that can be done here. Vegetation monitoring. By using bands such as the red and infrared, the data is often used to calculate the vegetation indices like NDVI, which helps in monitoring the plant health, crop conditions and land cover changes. The land surface analysis. So surface reflectance data is invaluable for the land cover classification and soil moisture estimation and studying the deforestation and desertification. Water bodies. Reflectance value can have used to monitor the water bodies, including changes in water quality, algal bloom and surface extent. Urban build-up area studies. It helps in distinguishing between the natural land and land cover and human-made structures. And last, the wildfire monitoring and the impact studies. So thanks for watching. In this video I have shown you the wildfire detection and vegetation change mapping using VIIRS and Landsat 8 imagery in Google Earth Engine. So thanks for watching, and the codes will be given in the description.